Hey guys, welcome. Glad you found the video. Today we're going to be talking about the law of conservation of energy. We have two major skills to go over today. The first is going to be finding the change of speed when we're dealing with gravitational potential energy. And the second is going to be how do you find the changes of speed when you're dealing with spring potential energy. Both of these involve the law of conservation of energy, okay? So let's go over that now. Well, what does the law of conservation of energy say? It says that your potential energy that you lose is the same as your kinetic energy gained. It also says that your kinetic energy gained is equal to your potential energy lost. There's a relationship here between the change in your potential energy and the change in your kinetic energy, okay? In fact, if we add these two together, we have a new quantity we call the mechanical energy. And I'll tell you this, the total mechanical energy of a system must stay the same. It must stay the same, okay? So what is total mechanical energy? Well, it's potential energy plus kinetic energy for a system. And the symbol for total mechanical energy is just capital E. Cut it off a little bit there. Okay, so there is a big caveat here. There's a big wrinkle. This is only true if we are not adding and we are not removing energy from the system. This is only true if no energy is added from the outside of the system and if no energy is removed from the system. We'll talk more about this later. But for now, we're going to make the assumption that no energy is coming in or out of the system. So the total energy of the system, total mechanical energy, will stay the same. There's an alternative way to write this, which we're going to be using today. The change of your potential energy is equal to the negative of your change of kinetic energy. And these two equations are equivalent to each other. Okay, let's move on. All right, so let's talk about the change of energy. Let's say you go to a skate park and you can't find any half pipes, so you're going to try out the quarter pipe. All right, so it looks like this, and it's got a long, kind of a sidewalk piece, kind of horizontal right here. And this is you. All right, and you're sitting up here at the top of this quarter pipe. You're ready to go down. Now, last class we talked about the potential energy. So we know we can actually calculate his potential energy if we know his height off the ground. So I'll tell you that now. It's 10 meters. And we can also find the potential energy if we know his mass. So you ask him his mass, and he tells you. It's 100 kilograms. Okay, why 10? Why 100? Because it's going to make our math a lot easier. So I go ahead and calculate his potential energy at the top using the MGH equation. Well, mass times 9.8 times height. His potential energy at the top is going to be 9,800 meters, or joules, excuse me. All right. What about at the bottom? Well, even though his mass stays the same and little g stays the same, his height is now going to be 0. So whatever's happening at the bottom, his potential energy is going to be 0 joules. 100 times 9.81 times 0. His height is 0 at the bottom. And we'll call this the initial state, and we'll call this the final state. So my question is, what's the change of potential energy? All right, it should be immediately obvious that your change of potential energy here, delta U, is equal to negative 9800 joules. That's it. That's all there is to it. It's subtraction. We've gone down from a higher place to a lower place. That means our potential energy, our gravitational potential energy, has gone down. 9800 joules is lost. But it's not actually lost. It's transformed into another form. In this case, it changes into kinetic energy. All right? How much kinetic energy is gained as it goes down this little ramp? Well, 9800 joules. All that potential energy that was stored up when he was climbing those stairs to get up the top of this quarter pipe, okay, all the energy that was stored has now been released. It's been taken out of the system, except it's not really taken out of the system. It's been transformed into kinetic energy. So his change of kinetic energy is 900 joules. He's gained 900 joules kinetic. He's lost 9800 joules of potential. Okay. So how do we find out his final kinetic energy? Well, we can do it pretty simply. We just add this 9800 joules to whatever you start out with. So, for example, let's say that his initial kinetic energy was 0. Let's say at the top of the ramp he's hesitating, so he's not really moving at all when he first starts on his little trip. Then that just kind of implies that his final kinetic energy down here is going to be 9800 joules. Pretty straightforward. What if his initial kinetic energy was, let's say he was moving a very small amount. Let's say it was 200 joules at the top. Well, we just add the 9800 to that, and now his kinetic energy at the bottom is going to be higher, of course, because he started out with kinetic energy. So at the bottom it's going to be 10,000 joules, okay? And so on. No matter what it is at the top, it's going to be 9800 joules more at the bottom. So in other words, he goes down this quarter pipe, he's going to be going faster. Now we've made a couple assumptions. Well, we made one major assumption here. We have assumed that no energy is lost. Okay? So there is no friction here. There is no drag. There's nothing like that. He doesn't hit any pebbles on the way down. No energy is lost between the initial and final states. Now, I want you guys to think about something. Okay? In this example, we have implicitly set y is equal to 0 at ground level. Okay? Wherever this long kind of sidewalk piece is right here. But in physics, you can set your origin to be wherever you want. So what if instead we had set y is equal to 0 up here at the top level of the quarter pipe? How would that change the problem? Would that make your delta U different if you made y equals 0 at the top of the ramp? Okay? So I want you guys to think about that. If we change where y equals 0 is and put it at a different place, is that going to change? Is that going to make the delta U end up be different? Okay? Think about that. All right. Now we'll do a real example. Okay. So it wouldn't be much of a quarter pipe if it just ended up on an infinite sidewalk, right? So let's say he continues to move and he reaches a ramp right here. Like so. So he's coming in from the left. All right, and he has an initial kinetic energy. Well, his spine's a little broken right here. Don't worry about that. Okay, so he's coming in like this, and he hits this ramp, but he leaves the ramp. Oh, excuse me. He leaves the ramp with a certain speed. So he hits the ramp, he's still going, and he's going to go up a bit, and then eventually come back down. All right? In this problem, this is his initial state, and this is his final state right here. The very moment when he leaves that ramp on the way up. So, in this example, our question is, given that his initial speed is 6 meters per second, and given that he flies up vertically off the end of that quarter pipe or ramp at 4 meters per second. Given this, and given this, and given that his mass is 50 kilograms, we want to know what's the height of this ramp. And amazingly enough, we can actually solve for the height of this ramp without knowing anything about the shape of this ramp, without knowing anything about anything else in this problem. We're going to solve it using energy. Okay. So first of all, what's our main assumption? We are assuming that no energy is lost. So we're assuming his skate wheels are they have no friction. We're assuming there's no friction here or anywhere on the ramp. There's no drag with the air. No energy is lost from the system. Okay? Okay. Well, first of all, what's his change in kinetic energy? All right? We can't just subtract 6 and 4. We have to convert this into kinetic energy and then find the change. All right? And this is probably going to be the only mildly tricky part. We're trying to find his change in kinetic energy. Well, let's see. His initial kinetic energy is 1/2 times 50 his mass times 6, which is initial velocity squared. Okay, so I'm totally doing this in my head right now. It's 900 joules. That's his initial kinetic energy. We would expect after going up that ramp, some of his initial kinetic energy is going to be stored as potential energy. So we're assuming his kinetic energy is going down. In fact, we don't really need to make the assumption since we know he's at 4 meters per second here. That's slower. So what's his final kinetic energy going to actually be? Let's find out. Final kinetic energy is 1/2. Mass is the same. Final velocity is 4. So his final kinetic energy is going to be, I'm totally doing this in my head right now. I do not have this written down in any way, shape, or form. All right, 400 joules. All right, well, it did go down. Just by looking at it, your change of kinetic energy is negative 500 joules. 500 joules of kinetic energy have gone somewhere. Where has it gone? It's been stored away as potential energy as he increases his height. All right, so I guess our job now is to find his change of potential energy. Without even writing down an equation, I already know his change of potential energy is positive 500 joules. He's gained 500 joules because it came from his loss of kinetic energy. All right, so our job now is to find the height. What I'm going to do here is I'm going to find his final potential energy and compare that to his initial potential energy and just go from there. All right, what's his initial potential energy? Well, if we set y is equal to 0 at ground level, his initial potential energy is 0 joules, mgh. Height is 0, 0 joules. What's his final potential energy? Let's see. Well, you know what? I already know it. It's got to be 500 joules. You start at 0, you added 500, it's got to be 500. That's your final. Now, we can use this to find the height, because 500 is equal to mgh, where h is his final height. We can definitely find h right now. Mass is 50. G is 9.8 or 9.81. Depends on how precise you want to be about this. And h is the unknown. Do a little algebra, solve for h, and you get the answer to the problem, 1.02 meters. Look at that. Look at how nicely that worked out. Now guys, I want you to kind of realize how simple and straightforward the energy part is on this problem. Look, 900 minus 400. We get negative 500 as your loss of kinetic energy. 500 joules. That's the energy part of this problem. It's super simple. The only part where there's any possible trickiness is converting between kinetic energy and velocity, and converting between potential energy and height. Okay? The underlying energy problem is very simple, given this assumption. All right, now we're going to try a spring type problem. Okay. I don't know why, but people who write physics problems really love this one right here. So you got a wall, you got a floor, you got a nice spring right here, and the spring has some sort of stopper plate right here. Naturally speaking, if this spring is kind of at rest, so it's not compressed or stretched at all, this right here, this is going to be its natural resting point. So it's just waiting right here. We're going to set that equal to 0. And this is our x-axis. So in the initial state of this problem, we got a little cart. It's rushing to the left. It's got some sort of initial velocity. And let's see, it's a 2 kilogram cart. We also know that the spring constant, we also know the spring constant is going to be 1,000 newtons per meter. Newtons per meter, excuse me. That's your K. The question here is this. So this cart is going to rush forward, it's going to hit this spring, and that spring is going to be compressed. When that happens, the kinetic energy of the cart is going to be turned into the stored spring energy in the spring. In fact, I'll draw a picture here of the final state of the system. All right, there's where it was. This cart has slammed into the spring, and it is now compressing that spring. And we actually know what the amount of compression is. I don't know, someone took a picture or something, and it turns out to be 5 centimeters. So this car, it reaches a maximum depth into the spring of 5 centimeters, and then it stops momentarily. You know, you guys know what's going to happen next. The spring is going to push it back, and it's going to bounce back off. But here, this is going to be our final state. This is our initial state. We're not worried about what happens after this for right now. Okay, so what is the problem? The question is find the initial speed of the block. And the cool thing about this is, you know, we don't have to set up some sort of crazy kinematics equation. We don't have to find like the force of the spring and integrate it or anything like that. All we need is energy. We're going to solve this problem using energy, and it's going to be pretty straightforward, actually. All right, so first of all, what's our strategy? Well, let's think about the kinetic energy and the potential energy and how it's changing. You're changing kinetic energy? Well, the little car is going fast, and then it's stopped in the final state. It's going to be negative. It's losing kinetic energy. What's your change of potential energy? This is spring potential energy, of course, not gravitational potential energy. Well, it's got no stored energy here. You compress a spring, you're storing energy in it. So it's going to be positive. It's gaining stored energy. And of course, we're making an assumption here that there's no friction whatsoever, and there's no energy lost from the system. All right, so let's get to work solving this. Well, let's think about how our kinetic energy changes. So we're going from initial kinetic energy to final kinetic energy. Well, our final kinetic energy right here, even though we know it's going to bounce back, at this split second in our final frame here, our final kinetic energy is 0. What's our initial kinetic energy? Now, we don't know that, but we can write an equation for it. 1/2 mv squared. I'll put a little bracket around it just so we know we don't know this yet. What about potential energy? How does potential energy change? From initial potential energy, oops, that is a U, not a V, to final potential energy. How does this change? Okay, we know our initial potential energy is 0. There's no energy stored in a spring that's not stretched or compressed. And our final potential energy, well, we'll use a potential energy equation for a spring. And we'll put a bracket around here because we haven't solved this out yet. So let's do this because we want to find our change of potential energy. And in this case, we know our change of potential energy is just equal to our final potential energy here. It's the potential energy the spring has right here. Let's find the final potential energy first, and then we can find the velocity. Now, I'm going to have to lose this diagram to get a new sheet. Sorry about that. Okay. If you miss a diagram, you can always go back. All right, so our job is to find the final potential energy. The energy equation for a spring, it actually kind of looks like the kinetic energy equation because it's 1/2 something times something squared. Let's see, K, that's 1,000 newtons per meter, excuse me. And of course, the compression is 5. All right, did you guys see that? It is not 5. We cannot use 5 for this problem. We have to convert it from centimeters into meters. You've got to watch out for that sort of stuff. Now we can solve it. All right, 1/2 times 1,000, that's 500, times 0.05 squared. Well, that's a nice result. It's just 25 joules. One thing I don't like about the examples and problems in your textbook is that they always use numbers that aren't exactly nice. So they wouldn't use 1,000 joules or 1,000 newtons per meter for their K. They'd use something like 1204 or something like that. I don't know why they do that. I don't like it. Okay. Hey, look. We know the final potential energy, so we know the change of potential energy. It's got to be plus 25 joules. It's gained 25 joules of potential energy. So immediately, we know that the kinetic energy has decreased by 25 joules. It's lost 25 joules of kinetic energy. Check it out, guys. Since the final kinetic energy is 0, we can automatically know that the initial kinetic energy was positive 25 joules. And guys, this is very lucky because kinetic energy cannot be less than 0. You can't have a negative number for kinetic energy, okay? So if you get a negative number for your kinetic energy, you're doing something a little bit wrong. Okay. All we have to do now is find out what V had to be, knowing that the initial kinetic energy was 25 joules. We know the mass, so this is going to be very straightforward. All we do is set 25 joules is equal to 1/2 times 2 kilograms times velocity squared. Okay? Do some algebra here, and we get V is equal to 5 meters per second. Look at that. So again, the energy part of this is very common sense. You know, we find out the change of energy, and we know the change of energy for potential has to be equal to the change of kinetic energy, just the opposite sign. Yeah, so that's pretty much it. All right, guys, so I want you to think about this. What if you were to combine two types of potential energy? What if you were to have a problem that combined the spring potential energy and the gravitational potential energy? Well, in that case, your change of potential energy would be equal to the change of spring potential energy. Oop, that's not what I meant to do. Okay, it'd be equal to the change of spring potential energy plus the change of gravitational potential energy. All right. If you want to look into this more, and I recommend it, in your book there's the active example 8.1. Okay, that's going to be on page 232 or 234. Excuse me. All right, that looks into a situation where you have a spring that's pushing a block straight up. So that's a combination of these two. Okay, and that's it. All right, guys. Thanks for watching.